Hello everyone, I hope you're doing well. So this is us continuing with Unit 2. We're well over halfway now and we're going to be looking at soaps and detergents. So you know the structure of the lessons by now. We will go through some prior knowledge questions to get your brain in gear, and then we've got some sort of the questions that you can expect to see. A little bit of theory. You can stop and pause the video whenever you wish to go through the questions, then the answers will appear later. When you unpause it, and then towards the end we've got some past paper questions to show you the sort of things that you're going to be assessed on. So you may want to pause the video here. This is the success criteria that we're going to be covering for the next, however long this takes you. So pause the video, have a read of these, and then we'll crack on with the prior knowledge questions. Okay, so take a look at this. This is going back to, this is Unit 3, a little bit of bond enthalpy. Pause the video here, and then when you're ready, the answer, if you want to pause it, the answer will then appear. So here we have, you're looking for now which of those two, the H2 or the I2, has got the lower bond enthalpy, because that will be the one that will break first. If you add heat energy to this mixture here with H2 and I2, and then the 2HI as well, I suppose, if you add heat energy to that, the one that has the lowest bond enthalpy would be the one that breaks first. Okay, moving on. So again, pause it, and when you're ready, come back and have a look at the answers. Okay, here we go, take yourself through this. Guess what's important to note here is for the marking instructions, to get both marks, you have to mention the polarity of both of the chemicals, not just one. So compare and contrast. Okay, moving on. So this now is the most recent work that we've done on fats and oils, and this will then build on to what we're going to do today. So take your time with this, go back and look at your notes, please don't rush through it. It is really, really important that you take this part of the lesson seriously. So if we have a look at the marking instructions here, so pause this if you wish and then read through it, and then we'll have a quick discussion about it. So we learned last lesson, or last time before Christmas, due to the different levels of saturation, you can have the different type of packing. So if you have an unsaturated fatty acid in your fat molecule, or fatty acids rather, then those molecules are going to pack really quite close together. You're going to get strong intermolecular forces, whereas that's the other way around, isn't it? The unsaturated ones are not going to be able to pack close together due to the kinks and the bends, due to those carbon-to-carbon double bonds, so they will have weaker intermolecular forces, whereas the saturated ones are going to have more intermolecular forces, because they're going to have more straight chain hydrocarbon tails, fatty acids, and therefore they will have stronger London dispersion forces, which is why their melting and boiling points will be higher. Okay. So this is us now properly started, soaps and detergents. We're going to look at how soaps are made by something called alkaline hydrolysis. We are going to explain how soaps can work, and then we're going to move on to the second sort of section, which is all to do with detergents. We're going to look at something called hard and soft water, and then explain why detergents must be used in areas with hard water. So these now, the next, are the sort of questions that you can expect to come across. So pause this, have a quick read. This is the sort of thing that you'd be expected to answer towards the end of the lesson. Okay, so a few questions here to get you going. So which group of these chemicals does the following molecule belong to? How is it made? How is it broken down? And what is the name of the alcohol produced when this is broken down? So again, pause this, go back through your notes to look at the fats and oils section, that might help. And then we'll go through the answers in a second or two. Okay, so hopefully this is familiar. This is a triglyceride. This is the fat molecule, and in there we have three ester groups, the Q group. So this therefore belongs to the ester homologous series. The way that we make it is via a condensation reaction. A specific type of condensation reaction is known as an esterification reaction, and it is between glycerol and 3 fatty acid molecules. We break this down and back into the glycerol and fatty acid molecules via a process called hydrolysis. And what is the name of the alcohol produced? Well, its common name is glycerol, but its systematic name is propane 1,2,3-triol, and we're required to know both of those names there, and also the structure as well, if you can remember from before Christmas. So this is relevant to today because we're going to use these fats and oils to make soaps. So let's go through this here. So a little bit of background, a little bit of history. We have evidence that soaps have been used since Babylon, Babylon, which is the biggest city of its time in the world. It's in modern day Iraq. It's now a ruin. You may have heard of the Hanging Gardens of Babylon. They're shown there in the background. And a famous gate there, the Ishtar Gate. And on a clay tablet that was found in modern day Iraq, there is a recipe for how to make soap. So that's not to say this is the first time that soap has been used, it is just the first recorded instance of soap. And the way that it was made is pretty much the same way that we make soaps nowadays. So how soaps are made, or how they were made in the ancient times, is that you would get fats and oils, and depending on where you are in the world, that might be olive oil if you're in the Mediterranean, for example, or it could be an animal fat if you don't have access to that there. You would take ashes from wood, for example. You would react those together with a little bit of water as well, and then you'd get your soap, which would be used for cleaning your clothes, cleaning yourself, cleaning anything that was required. Now, the chemistry behind this, there's something in the ashes. There's something in the ashes which is actually helping the fats and oils to break apart and to form into soap. And that something that is in the ashes is a base, and it's that base that is required to take that fat and oil molecule and break it apart to form the soap molecule. So we're going to look at that in a bit more detail. So looking at the chemical structure of a fat and oil, it looks like this here. We've seen this before. We've got, in this instance here, we have 2 different types of fatty acids. Sometimes they're all the same, sometimes they're all different. But in this case, we've got 2 different types of fatty acids, slightly different length of carbon chain. We would react that with water, and this is the hydrolysis part. So the fat and oil is hydrolyzed, and it produces glycerol and fatty acids. Now we require a base, and if we add a base, in this case the base is sodium hydroxide, well, that's going to neutralize the fatty acid and it's going to produce a soap. Now if you have an acid and a base reaction being reacting together, you're going to produce a salt. So the salt here is the soap, and this process is known as alkaline hydrolysis, or you may see it referred to as saponification, which is basically meaning making soap. And if you look a little bit closer at that soap molecule, we start to build up an idea as to why exactly, or how exactly, soaps can clean things. So here is in this case, this is an example of sodium palmitate, so it must be palmic acid, I guess, palm oil, I guess, would be used as the fatty acid, the oil for this here. And if you show it in the skeletal structure there, we have our covalent hydrocarbon tail, and then we also have an ionic head. Which parts of that molecule there are polar and which are non-polar? So pause this and take a second to have a think about that, please. So the non-polar section is that covalent hydrocarbon tail. Now we can refer to this as hydrophobic. The phobic bit means we can think of it as being scared of or being afraid of. And what that translates as, hydrophobic translates as scared of water. So we're going to use that term again. The polar section is the head, and we would refer to that as being hydrophilic. In other words, it likes water. And that's relevant, that those 2 sections give soap the cleaning action, the non-polar hydrophobic tail and the polar hydrophilic head. So let's have a look at this in a bit more detail as to how soaps actually clean things. So we've got an example here whereby we have a stain, and the stain in this case is oil-based or grease or whatever. But the point is that it is a non-polar, and on this diagram here it's on a cotton fabric, but it could be on your pots and pans or your hands or whatever it is. It doesn't really matter. Our soap molecule here has got two sections, as we've already said. We've got a polar head and we've also got a non-polar tail. What do you think is going to happen when that soap molecule, which is, it should be made clear, is suspended in water? What's going to happen when that soap molecule gets close to the oil? So pause and have a think about what might happen. So what does happen is that the non-polar section, the covalent tail, the hydrophobic section of that soap molecule, dissolves in the non-polar oil. We can refer to this as like dissolves like. Now, if you agitate this with a little bit of scrubbing, maybe it gets bounced around inside a washing machine or whatever it happens to be, maybe that little ball of oil starts to sort of lift up a little bit, and as it lifts up, more and more of these soap molecules the covalent tail starts to dissolve into the non-polar stain, the oil or the grease. And when that happens, we get something like this being produced. So now we produce something called a micelle, and in our micelle we have the ionic head on the outside and then the covalent hydrophobic tail on the inside. And this now is suspended in the water. It's been lifted off the surface, the pots and pans or the clothing, whatever it is, it's been lifted off the surface and it's now suspended in water. And this can now just be drained away. And all throughout your water here, you would have many, many, many of these micelles floating around, which would then be rinsed away. And this is how soaps work. It's also relevant to what we're going through at the minute with the pandemic. You know that every time you enter the science classroom, you have to wash your hands and use plenty of soap and water. And the reason for this is because of how the virus is structured. So on the inside there, that purple structure there, that's the genetic DNA there, or the DNA. And then the outside, the yellow bit there, well, that's represented that's the outer casing. That's what's known as a lipid or a fat membrane. And that fat membrane there, if you add soap to it, well, the non-polar sections of the soap molecules will dissolve into the lipid, the fat non-polar membrane, and then we'll break it apart. And by breaking apart that virus, it then cannot replicate any further, and it prevents it from doing its work. So a little bit of relevance to what we're going through at the minute. Now we're coming to the thing that you'd be asked to do in your tests and your exams. So explain fully how this particular soap molecule acts to keep grease and non-polar substances suspended in water during cleaning. So pause this, give yourself 5-10 minutes or so, and it's an essay question, so quite a long one. So give yourself some time and then have a look at the answers that will appear in the next slide. So you need to mention the following 3 things. So again, pause this and tick off and see how you've got on. Okay, so moving on to detergents. This won't take too long, we do quite quickly. So if you look at the type of water that you can get in the UK, you will get different types of water. You can get hard water or you can get soft water. So up in Aberdeen we have soft water, but if you were down in London, you would get harder water. And the difference between the two is the type of minerals that are dissolved into that water. So hard water will have mineral ions such as calcium and magnesium ion dissolved into them, and that may come from the rocks that form the riverbed that the water has travelled down, or maybe it's the piping that is making up the system down in London. Whatever it is that the calcium and the magnesium ions are dissolved into the water. And that's a bit of a problem because soap doesn't really work too well in hard water. So what you want with soap and soft water is when you add them together, you will get a lather, and that lather can then be used for cleaning. But if you have hard water, you won't get that lather. You'll get something called a scum, which is basically an insoluble precipitate. And we can see this if you were to have soap into trying to clean some dishes. You would get this scum on the outside of this insoluble precipitate on the outside of the surface that you're trying to clean. So the chemistry behind that is what the bit that we're really interested in. So let's take a look at that. The way that detergents work is that their ionic head is slightly different, and being slightly different, it can react in a slightly different way and produce a different product. So this is our soap molecule here, and with our ionic head here, so we have a sodium and a carboxyl group there, minus the hydrogen. That will react with the Ca2 plus and the Mg2 plus, depending on what the mineral ion is, and it will form an insoluble precipitate. But if you use a detergent, it has a very slightly different ionic head, and that ionic head will produce something different. It will produce a soluble solution which can then be rinsed away, and it will produce a much better cleaning effect. Okay, so that's us done. So explain how soaps are made by the alkaline hydrolysis of fats and oils. In terms of the polar and non-polar parts of soap, explain how they clean materials. Define hard and soft water, and then explain why detergents must be used in areas with hard water. If you didn't get any of those, you want to go back over, obviously you can do that, that's quite easy. There should be timestamps below so you can have a look at those. But let's go through a couple of past paper questions to see how you got on. Okay, as usual, pause this when you're ready, take a look at the answer. Okay, so we've got our soap node, we've got a fat molecule there, and that's reacting with 3 molecules of, or 3 moles of sodium hydroxide. And this is an example of a hydrolysis reaction, specifically alkaline hydrolysis. So the answer is C. Next question. Which of the following is the salt of a long chain fatty acid? Well, the answer to that one is the soap. The fatty acid would react with the base, sodium hydroxide, and it would therefore produce a salt. So the salt is the soap. Next question. So this is the one I showed you at the beginning. If you can pause and have a look at this, maybe you can sketch this on your pieces of paper or whatever you're using. So your drawing needs to show the covalent tail is dissolved into the grease or the fat soluble dirt, and then the answer for the section is that it is hydrophobic. Okay, so there's a little bit of problem solving here. So have a go at this, and then we've got another question which will come up in the next slide, and then the answers will come up all together. Okay, have a go at this, and then that is us pretty much done. Okay, so that's us done. That's the first lesson done of lockdown number 2. If you want to please complete the corresponding worksheet for this, get that back to me as soon as possible. And if you have any questions at all, let me know and I'll help out to the best of my abilities. All right, thank you.